So let's look into now that system call issue. Previous session we stopped at that system call. We have understood that system call cannot be invoked just like a function call. What we'll do this session, we'll take a look at how to invoke a system call. If you have to write code and application to invoke a system call, how would you do that? Take down the steps. Invoking system calls. So how to do that? Carefully understand this. These are the steps. There are 4 different steps that we need to write code for. And these 4 steps will help the application invoke a system call. The first step, carefully watch those steps, it will be easy slowly. Every system call is identified by a unique number in the kernel space. Say for example, there are 100 system calls. Each of those 100 calls has a unique identifier. So step 1 is you need to copy the identifier of the system call which you intend to invoke into an accumulator called EAX. It means the application developer must know the identifier number of a system call that he wants to invoke. So step 1 is to copy that identifier into EAX or the primary accumulator. In case of Intel 32, EAX. The second step is what did we do in the case of arguments earlier? Normal function call, we copied the arguments onto top of the stack. System call, we copy the arguments into processor registers, into accumulators. Because that is the common area which kernel space and user space code can access. So what we should do, starting with EBX. In the case of Intel 32, we have EBX, ECX, EDX, EIX. Like this, in this sequence, we have 6 more accumulators. We can copy all the arguments into these accumulators. Again, the same pattern, starting with the rightmost, moving towards the left, transfer each argument onto accumulator. In the case of function call, we transfer it to stack, user mode stack. The third step is you should initiate an exception. Exceptions are also called software interrupts, or they're also called programmed interrupts. So you should initiate one software interrupt on the processor. Generally this interrupt is referred to as trap. Right? So we should initiate one trap exception using architecture specific machine instruction set. That is number 3. And number 4, we have to read the exit value of the system call back from EAX. Obviously, step 4 will execute when system call returns. Step 3 will push the control into kernel mode, and step 3 will ensure system call is executed. When system call returns, the control is back into the 4th instruction there. So first take down those steps, we will look into the execution part. Invoking, how to do that. So now, the assumption is this. The assumption is, I want to call a system call with ID 338. Okay? Now, let's apply those steps. What is step 1? Copy that 338 into EAX. So first instruction there you can see, mobile 338, dollar there refers to constant. So 338 into EAX, that is step 1. Step 2, watch that function call there. Watch that function call, it doesn't have any arguments. So I'm skipping off step 2, no arguments being passed. Okay? And then I've got the third step. What is third step? Initiate an exception called trap. There are multiple ways of doing this. What you're seeing is basically traditional approach. Of late, in the latest processor codes, you have instructions called sysenter and sysexit, using which you can do the same. But I'm doing it in the traditional instruction set approach. The instruction is called INT. INT will generate a software interrupt on the processor. It triggers an exception on the processor. We intend to generate an exception called trap. For a trap exception, there is one descriptor code called 0x80. So interrupt at 0x80 will trigger trap. So that's the line that's causing the trap exception to occur. And the last step, we intend to move the result into that local data ret. Whatever system call returns, we intend to hold that value in that local variable return int ret. So I've got moval EAX is where you find the result, the return value. I'm moving the return value back from EAX into -4. So now, carefully understand this, beginners. I should not call function like this, rather this code should be replaced here. If you make a function call, what will happen? Compiler will translate that into call instruction, isn't it? Call instruction requires both the functions in same code segment. So you should not call the function now. This should be replaced with this code. This should be replaced completely with that code. So I'll show you furthermore. Okay, we'll look at that logic in a minute. Watch this one. You should be able to guess now. Take your time, understand the program. What are we doing in the program? Very simple. We have main function calling a function called lsproc. That particular function lsproc on top is implemented. What is that function doing? It's calling a system call with ID 349. So no arguments. That's the reason why the second step is left out there. Because the function doesn't have, system call doesn't have any argument. So 349 system call we are trying to invoke, and as you've seen earlier, the same sequence of steps now. So this is how you put assembly instructions into source functions. And this is the only way, this is the only approach of calling a system call from the application. Okay, first if you want you can take down the example code, beginners. This is the only way to initiate a system call execution or system call from the user mode. Application will have to transit into kernel mode to execute this. How the transition happens, we'll check that in a few minutes. Only those 3 instructions would be enough if you want to just take down the system call invocation part. lsproc routine would be enough.
Can you explain this interrupt again?
Int is an instruction that generates an interrupt, a software interrupt. And the software interrupts are of different types. We intend to generate an interrupt called trap. For each of the software interrupts, there is one vector number assigned. 0x80 is a trap interrupt exception.
That is documented in
the instruction set manual of the processor. Int is directly a machine instruction. So this is the only possible way of invoking a system. Actually what I did, we have added the system call 349 to kernel source code. We have compiled the kernel with that system call, and then we are invoking it. I haven't shown you how to add, but we'll look at that in a few minutes. Up to here clear? Now, let's make an assumption like this. I want to call the same system call 349 in 10 other applications. This is one application assumed like this. In 10 other application implementations, I intend to call this system call. Will I have to repeat that code? What are the options then? This is the only way of calling a syscall. So what are the options with me? Do I have to repeat the code again for all the 10 times? Or is there any possibility of reusing this? Can I reuse this function? Yes, 2 ways. You make this a macro. We can make this a macro, isn't it? These 3 lines can be put into one macro. And wherever I intend to call, in the same application, if I intend to call the same system call all over again for 10-20 times, each call I'll do with a macro. That's one way. If I want the same system call to work in multiple applications, I can take that function lsproc and put that into an SO file. Isn't it? But this SO file I can link it to 10 different applications and call lsproc. Okay, like this. This single function now I can use whenever I intend to invoke system call 349. Okay, clear? Such kind of functions that you're seeing there, those are called APIs. So APIs and system calls are not same. Those of you who have some experience of programming, you might have used read write and thinking that they are system calls. They are not. They are APIs like this. Invoking a system call requires assembly instruction set. There's no other way of doing it. So either you write it on your own or call a function which has such instructions already in it. So APIs are functions which have these instructions in them. If I want to reuse this system call, or if I want to invoke this system call, I'll have to take this, push this into a library and use it wherever I want. So such kind of functions which have inline assembly code and which are programmed to invoke a system call are called APIs. Now that is the conclusion point. So most of you might have had a question. We are calling system calls in our programs. We never use this code. We are actually calling APIs. Who provided you APIs? The standard C library, or sometimes the OS specific library. Some SO file, isn't it? So there's some SO file in every operating system giving you such functions. And that's the reason we never encountered assembly code directly. We never had to use it directly. Okay, check down. It is a standard practice, just a point, it is a standard practice to use APIs for invoking system calls. To use APIs for invoking system calls. What are APIs? User space functions that contain inline assembly code to invoke system calls. APIs are user mode functions. APIs are user mode functions that contain inline assembly code. APIs are user mode functions that contain inline assembly code to invoke system calls. Inline assembly code that invokes system calls. How it works, we'll see that in a minute. So who should provide APIs now? For writing code to invoke a system call, we should know IDs now. For IDs, you should know kernel code. Obviously now, the APIs should be provided by the kernel vendor, the OS vendor. Third-party developers cannot write APIs because usually these IDs are not published. These IDs are not documented. So obviously now the OS vendor should provide APIs. In case of Linux, there are standards called POSIX, BSD, System 5, according to which the APIs are implemented. We'll touch on that part a little later. But the APIs should be provided by the OS vendor. Now carefully understand this. If your application calls an API and invokes a system call, will the usage of API make your application OS specific? Take your time analyzing the answer. Invocation of the API or using the API in your application, will that make your application code OS specific? Yes, because if you're trying to move that code onto some other OS and trying to build it, you will not be able to link with that API because APIs are specific to OS. So the benefit with API is you can call system calls. But the problem with APIs is APIs make up or end up your code as OS specific. Say for instance, I intend to invoke a system call, but I don't want my code to be bound to an OS. What is the possibility then? Can you think of any method of doing this? I intend to invoke a system call, I intend to use an API also for that, but I don't want my code to be specific to that particular OS. Is there any way of writing neutral code which still can use APIs? What I mean by neutral code is OS neutral code. Take a time. Is there any way of writing OS neutral code in your application that can still use APIs, but the code should be completely OS neutral? Simple technique, very simple. Have your own library designed. Create some functions of your own name, with your own naming convention. Design your own functions. Let those functions call APIs. In your application, use those functions. Now, for Windows, you create one library with the same name functions. For Unix, you create the same library with same name functions. Windows version library will call Windows APIs. Unix version will call Unix APIs. Your application will call these functions, not the APIs. So application now can link with Windows version library as well as Linux version library without any changes to your code. We are simply abstracting APIs and creating a wrapper function above them. Got it? Clear? Isn't C library doing that? Printf anywhere available. The version of printf for Unix is different. The version of printf for Windows is different. Malloc available everywhere. Version of malloc different for Unix. Version of malloc different for Windows, isn't it? So C library or standard libraries which come along with the compilers are nothing but wrapper libraries around what? APIs. You take a C++ library, C library, a Java kind of library. All these standard libraries are wrappers around native APIs. The usage, the benefit with such wrappers is they help you keep your code neutral to OS, so that you can move your code and compile anywhere. I'm not talking about binary portability. I'm not talking about compiling, building and the binary file being ported. I'm talking about source code being portable. If I write source code, I should be able to compile that on Windows, I should be able to compile that on Unix without changing it. You call printf, can you compile it on both? Yes. In place of printf, you call a system call, so API. Then you cannot compile it on Windows if you have used Unix call. And you cannot compile on Unix if you have used Windows call. So from application point of view, always you must make the choice. Choice 1, whether to call APIs directly. If you call APIs directly, then the benefit is performance will slightly increase. But the side effect is your code is always specific. Second option is don't call APIs. Use the APIs through wrapper interfaces. The benefit is your code is now portable. But the problem is there could be slight delay in performance. It's negligible these days, the performance delay, because of the CPUs we have. So this is the conclusion now. Carefully watch this table. You'll understand different modes of programming. Always this is what we do generally in the case of normal C programming. We write an application, we usually make use of the standard library, isn't it? That's coming with the compiler. Most of the standard library routines call APIs. APIs call system calls. What are system calls? They're kernel functions, right? But what is their functionality? Their functionality is to serve as an interface for the kernel service. There is some memory management service, process management service, inter-process communication service, and driver service. For applications to access this service, they must go through a validation layer. That validation layer is system call. So system call is not the end functionality. System call is a means of accessing kernel service. So you see now, ultimately, the entire functionality is where? In the kernel service, that could be a driver, whatever, it depends on which call you're using. So application from the user mode can transit into kernel service through language library, which is a wrapper around API, API around system call, an interface for service. This is option 1. What is this one? I'm skipping library here, directly calling APIs and then system call and then kernel service. Is it possible to skip API also and use your own assembly code or to implement your own API code? Yes, either way it is same. Either you write assembly code on your own or you reuse a function that has assembly instructions in it. Either way API is there, isn't it? So this is option 1, this is option 2. Pros and cons, I told you. What are pros and cons? What will be the stack frame here? Applications, main function probably calling BRK. One function call, one stack frame. And then you are into kernel mode, isn't it? What about stack frames here? Multiple. So performance will slightly decrease. But that is negligible with today's computing power. But the benefit is code is neutral. Take down the table. Beginners, take down this table. This is very important generally to define also. What is system call? What is its role? System calls are kernel functions which are meant to serve as an interface for services. So system calls are not the end functionality. They are simply interfaces. The last, the tree on the leftmost part is important. The rest of it is up to you. If you want to document it, you can, otherwise you can skip it off. So now, which path will you take? It depends on what. Will you go with the first type or the last type? It depends on what. What criteria will you choose which type to go? If you're writing an application, will you go with the type 1 or type 2? Only criteria is portability of your code. If you are not intending at writing code that is meant to run or compile, built on multiple platforms, it's always better to go with APIs. Okay? If you intend to write source that is built and compiled on multiple platforms, you must go with wrapper libraries. That's the only way of choosing. Clear? Up till here clear? Okay. Please carefully understand one more point. These are all basic questions. Very simple basic questions. Application developer, if he knows, can have his own inline assembly code and call a system call like we have done earlier. I will test and show you that in a minute. And also he can use ready-to-use APIs. Right? So OS may provide a library of APIs. He can call the API functions and invoke system call without writing assembly code. Or, like we have seen earlier, he can put in some assembly instructions and then call system call. What is the difference and which should be standard? What should be encouraged and what should not be? Let's try and write down some points about it. It is about invoking a system call from the application directly versus using an API. This is a very important question in most of the beginner interviews. If you know how to call a system call, will you write an application to call a system call on your own without using APIs? And what will be the side effects or benefits of such an approach over using ready-to-use APIs? Okay, take down. Which one is better? Which one you think is a better approach? Why is ready-to-use better approach? Okay, if it is ready to use, what could be the reason you're choosing ready to use? Can you justify your reasons? Dynamically linked at runtime, okay. What else? Okay, we'll document those. 3 reasons for which you should go for ready to use. Take down. Applications should avoid invoking system calls. Applications should avoid invoking system calls directly using inline assembly instructions. Directly using inline assembly instructions. That's the first point. Next point. Using OS specific using OS-specific ready-to-use APIs, using OS-specific ready-to-use APIs is always preferred, OS-specific ready-to-use APIs is always preferred for the following reasons. 1. Please carefully understand the reasons. System calls residing kernel space. Now kernel space code can change between version to version. Say in version 1 of the kernel, a system call has 3 arguments. In version 2 of the kernel, the same system call can have 1 argument. System calls are not intended to retain their interface between kernel versions. There is no such guarantee. So if you call a system call directly using your own assembly instruction, what will happen? Say version 1 of the kernel, you wrote system call. You wrote an application calling that system call. In that version you had 3 arguments, maybe you wrote the code according to 3 arguments. The same application now, if it is run on version 2 kernel, then there is a possibility the interface might have changed and the application will break. Okay? So there is a norm in kernel community. They do not guarantee the kernel interfaces to be same across multiple versions of same kernel, because their assumption is kernel has nothing to do with the application implementation. An application developer should not call kernel code directly without using proper interface. And that interface is API. So kernel code is implemented assuming that application always is coming to an API. Okay, that's the first reason. Take down reason 1. So if you do so, you are at your own risk then. Okay, if you do this kind of assembly instruction and then call system call, you will be at a risk because the application may not work on future versions of the kernel. So step 1, point 1. System call interfaces. System call interfaces. What we mean by interface is the function signature. System call interfaces are not same across multiple kernel versions. Actually, it should be, may not be same, it's not or not. System call interfaces may not be same across multiple kernel versions. System call interfaces may not be same across multiple kernel versions. What is the impact of this? Applications using a specific interface may not work on signature. If it is changed, your function is broken now. Okay, that is 1. Second, I'll first talk about this, understand this, and then if you want to mention about it. API to system call relationship. Always, the operating system specific API to system call relationship is not one-to-one. Is not guaranteed, it's not fixed to be one-to-one. It means, it doesn't mean that one API always will call one system call. APIs are mapped to services. Say a particular service requires 3 system calls. Then such an API will include code for invoking 3 system calls. If you call your own system call, then you have to make 3 different system calls and transit. Single API call, you can link code for 3 different. APIs always are mapped for functionality and not for system call. If 300 system calls are there, it doesn't mean that you have 300 APIs. Okay, so that's one more reason. So APIs always are designed by mapping them into functionality that you need. For that functionality, you may need one system call or multiple. API takes care of it. So second reason is that APIs are designed to provide a specific kernel service to application. APIs are designed to provide specific kernel service to application. APIs are designed to provide specific kernel service to application, which may involve multiple system calls. Which may involve multiple system calls. Which may involve multiple system calls. This is reason number 2. It means API to syscall relationship need not be one-to-one. It can be one-to-many. Now the third one is this. APIs are always implemented to optimize your kernel mode user mode transition. When you make a system call, the application is moving from user mode memory into kernel mode. The transition actually causes delay in execution. We'll see why in a minute. The transition from user mode to kernel mode always causes delay in execution. The more the system calls the application has, the slower the application will be. So now APIs are returned keeping in view this delay. APIs are designed to eliminate the need of multiple calls. Say for instance you call a function called BRK. BRK is an API to allocate memory. Malloc actually calls BRK. The BRK will not call the kernel function to allocate memory whenever you call BRK. BRK, what it does, when you call the first time with 100 bytes, it will fetch more than 100 bytes to keep it ready. Next time when you call, it will not go into kernel mode. It will fetch the memory from earlier fetched location. Similarly, if you do a file read, fread you have gone through maybe most of C libraries. When you do a file read, if you request 100 bytes of data to be read, it will read 300 bytes or 400 bytes. Next time when you call again the read call, there is no need to go into kernel mode. So APIs are always designed to optimize and eliminate or minimize system call transitions. In the process, they do data prefetching, they do lots of resource prefetching even before it is required. So that will eliminate the need of system call or system mode transition whenever application calls an API. Malloc is a very good example of it. When you call malloc in C library, if you pass even 10 bytes, it will get 128 KB. The next malloc call will never go into kernel mode. It will always allocate from that 128 KB. When that 128 KB is elapsed, it moves there into kernel mode. So there is a high possibility application using less than 128 KB of heap will make it with one transition. Okay, so take down that last point. APIs are optimized for performance. APIs are optimized for performance. APIs are optimized for performance. And they invoke a system call. And they invoke a system call only if it is. And they invoke a system call only if it is mandatory. So it's not that I'm calling API, system call will execute. Got this? There's no rule that if I'm calling API, system call will execute. It all depends on how you are calling the API, how many times you have called the same API earlier, all that. So whenever you call API, it doesn't mean you're going into kernel mode, because APIs are completely optimized. Clear? So those are 3 reasons why you must stick always to OS specific APIs, and you should not call system calls directly. But you should know the process. The reason why you should know the process is you should know that user mode to kernel mode transition is there. So until here, any questions, you can take 2 minutes. We have understood that code involved in invoking system calls, and then we have seen the possibilities of writing that code and reusing that code, and then we have understood which is the best approach. any questions up to this point? Clear now? Let's now look into the test part of it. I wrote an application, I wrote a sample code there, invoking system called 349 or something, isn't it? For you to carry out some lab exercise on this, some practical, we'll just run into one process. What I've done actually is I've added one system call to kernel source with that number 349. And then I wrote an assembly code to invoke it. The idea is to demonstrate the transition from user mode to kernel mode. What we'll do first, I'll show you the steps involved in adding a system call. If at all there's a requirement to add a new system call into Linux kernel, since the kernel source is open, you can do it. Let's look at the steps involved in how to do this, and then we'll see how to compile and build that into a binary image, how to boot it, and then run the application that we have seen earlier to call that system call. This will help you understand the transition and test it firsthand, because the backend system call is ours, application is also our code. Instead of calling an existing system call, we'll do this. So now the steps are about how to invoke it, and how to add a new system call to kernel source. Those of you who are beginners, it's mandatory, you must carry out this exercise 1. So, steps to add a system call to Linux kernel source. Steps to add system call to Linux kernel source. For carrying out this process, you need to have a copy of the kernel source code. Kernel source code can be downloaded from kernel.org. If you have installed Fedora Ubuntu, you will not have kernel source code installed. Distributions don't give you source. They only give you binary version kernel that you could use. So you must explicitly download the kernel source, install it. When you download the kernel source, you get the source files in 2 formats. One is called a pzip, other one is called a gzip. Like for instance here, you can see here, I've got a file called tar.pzip2. That's a compression algorithm. So what you do is do this, tar, download the file and say tar xvf, x for extract, v for verbose. So tar xvf and the file. That file will elaborate, will unzip and create a folder, just like a zipping compression tool on Windows. Only difference is we're doing it on the command line here. So step 1, or the assumption for this case study is you must have source code with you, and all these steps I'm going to show you will be manipulating the source code, changes to source code. So we will be in the source tree to carry out these steps. In my case, I've got the source code in this folder. It is recommended to put the source code always in that folder. usr/src is meant for sources. The rest of the folder structure is meant for binaries, libraries and all that. src is meant to host source code. So any source code when you download, keep it there. That's a normal standard, normal convention. So I've got the source code now in usr/src. My source version is 3.2.0. I'll talk about the kernel version in pattern a little later. Right now I've got Linux source 3.2.0. Whatever steps you're documenting now, they are 3.0 kernel specific. So let's take down steps. Step 1. What is this about? Adding system call. So step 1. Reserve a new identifier. Reserve a new identifier for the system call. Reserve new identifier for the system call. That is step 1. So in step 1 what we do is we assign one ID for our system call, because every system call should have a ID. How we do it? Watch this first and then you write down. Watch this. This is how it looks like. Kernel source code main folder, the home folder looks like this. You'll find all of them, drivers, all the subsystems you'll find as separate folders. Memory management, process management, each of them is a separate folder. Okay? Now here, I'm doing some changes. you have to open this file for the step 1. So step 1 you wrote, under that you write down, open the file. Where is this Arch folder? Source tree. Your home folder should be source tree. Present working directory should be source tree. In the source tree, a branch called architecture. Right, so open the file, arch slash, you write down like this, $arch. It can be ARM, it can be PowerPC, it can be x86. Right now I'm doing it for x86. If you want to do it for an ARM, there you find a folder ARM in place of x86. Go into ARM folder. So right value you choose. To mention that, in the record you mention arch slash $arch. $arch is the value that you choose. In this case, $arch is equal to x86. Slash include slash ASM slash UniSTD means Unix standard. Unix standard underscore 32-bit. Because I'm trying to do this for a 32-bit processor. Unix standard underscore 32.h. For 64-bit kernel, you'll find a file Unix standard underscore 64. We are doing it for Unix standard 32. Because I'm using a 32-bit machine here. In this file now, you'll find this. So you must open this file. In this file, you'll find all the IDs. They're simply constants, nothing but constants. So you have to go to the end of this. We don't intend to change any of the existing. Go to end of this list and add an entry like this. Always follow the same naming convention. It's a macro, but even then follow the same naming convention. Linux kernel has a very clear, wide policy on naming conventions. So any changes to kernel code, you must follow the same naming pattern for readability purposes. So hash define is to define a constant, a macro, underscore nr underscore your system call name and then the ID. Take incrementally next number. So I've got 349, if you're taking one more it will be 350. What I've done, I've just made this entry earlier. So as a sample, if you want, you can take this line. Always go to the end, then add one more, take incrementally next number. I'll talk about that. First you take down this entry is done. The next change is, you'll find a counter here called nrsysconst. That is a constant actually, which is equal to total number of consts. You also increment that by 1. Whatever the value is there, you increment that also by. See, if you add 1, will the total increase? Yes. So you add 1 on top, increase the total. Don't assume that if I have 349, why is this 350? There is one extra counter added. So if this is 349, this should be 351. If this is 350 here, this should be 352. So increment, add your entry at the end, increment this by 1. Here, this is first change. Second step. So first step where we changed in a file called Unix standard 32.h. Second step, step number 2. The declared system call prototype. The declared system call prototype. Declared system call prototype. This step you must open the file, same path, same location, a file called syscalls.h. This is step 2. For step 2 you must open this file. So under that step 2 write down, open the file, take down the path as you have taken earlier. The file name is syscalls.h. Watch this. Inside this file now, you'll find 3 sections. Inside this file, you'll find 3 different logical sections. The first one is x86 32 and 64. So if you declare your function prototype here, that function will be available for both the builds. If you build the kernel for 32-bit x86, the function will be added. And if you build the kernel for 64-bit x86, the function will be added. Then you have one more section down there called 32 only. If you add it here, it will be compiled only for 32-bit build. And obviously the last one, 64 only, it will appear only in 64-bit build. When you compile the source code, you must select your build. Are you building kernel image for 64 platform or 32 platform? For test purposes, so what we do, we'll just have it here, common for both, for 32 as well as 64. What you should do is simply declare the prototype of your function. What is prototype? Signature and the arguments. Signature, which includes all written type and arguments. So do you find this? I've done this for the earlier call. I've declared the prototype. My system call name is sys_ls_proc. It takes no arguments, so void. It returns an integer, so int. But then there is one reserved keyword called ASM linkage. ASM linkage is a kernel reserved keyword. Kernel reserved keyword. You should use that with system calls. It's a good practice to start a system call with that keyword ASM linkage. It's actually an instruction to compiler. We'll talk about that in the execution part. So ASM linkage, first that as it is, then signature. Signature, your choice. Whatever arguments you want to accept and whatever you want to return based on that signature. Where did I put it? I've put that in the x86 32 and 64 section. So this will be added to both the builds, 32-bit build as well as 64-bit build. So any questions up to here, clear up to here? It's all changing source code. That's the reason why we have to do it in steps. Step number 3, the last one.
Where does this routine reside?
Well, let's go through the steps at the end of it, you know. Step number 3. Append system call address. Append system call address. Append system call address to system call table. Append system call address to syscall table. Slight change in the path. Slight change in the path. Arch x86 is common. If you choose ARM, ARM will be common for all the changes. Now, from include, we are coming to one folder called kernel. In the kernel, we are opening a file called syscall table_32 for 32-bit machines, syscall 64 for 64-bit machines. We are trying to carry out this for 32. So I'm opening 32.s. .s there indicates assembly source. Now this is a table, a data structure where all the system call addresses are stored. Okay. So now this data structure has records. How many records should be there? That should be equal to number of system calls. Actually, ID is for that purpose. ID is for selecting the size of this table. If 349 IDs are there, 350 calls are there, what should be size of this table? 350 records. Okay. Which number have we taken? 349. So open this. You'll find a table, a data structure. It's usually a vector. You go to the offset number 349. It's very important you choose the same offset. 345, 6, 7, 8, 9. If you have taken 350, the next entry. There you append the address of your function. What is the address of function? How do you represent the address of function? Function name. Function name at the compile time results in its address. .log is an instruction to assembler. So start with .log and then mention your function name. So what is the offset of that? 349. Now watch this carefully. When the API makes a system call, it is copying the ID into EAX, no? And then generating a trap. So the kernel code will look into 349 index of this table. That is the reason why the number should be stored in EAX. If you store a number 349, if you don't put the function address in 349, what will happen? Call will not execute, or a wrong call will get called. So it's very important you copy in the same index that you have reserved down here. So take down that last. If you want to take down, is that recording of .log is an instruction to assembler, and function name is sys_lsproc. Here. So up till here, first we have taken the ID, second we have prototyped it, and number 3 we have added the address of it into table. All these we have carried out in which folder? Which major branch? Arch. Arch was the major branch in which we carried out all this. Now step number 4 and the last step. Implement syscall routine. Implement syscall routine. Implement syscall routine. Now for this, there is no specific rule of way to carry out. You can add your system call to any location of kernel source tree. If your system call is dealing with memory services, go into branch and add. If your system call is dealing with drivers, go into drivers branch and add. It means there is no specific preset rule of where to add it. All the earlier steps must be carried out in the same files I mentioned. But step 4 is your choice. Wherever you want, you can add within the source tree. Okay? Now general standard is this. General practice is, depending on the call, they decide. Memory, as I told you, into drivers into drivers. Can you find a folder here called kernel? Most of system calls will be there in that folder. Mention now. Mention one note. Source code can be appended. Source code can be appended to any branch. Any branch of the kernel source tree. Of the kernel source tree. Next point. Once a branch is selected, once a branch is selected, system call can be appended. System call can be appended to existing sources. System call can be appended to existing sources, or system call can be appended to existing sources or implemented in a new source file, So here I have selected a branch called kernel. Now 2 options. Either you open any .c file here, go to the end of it, write your function. That's option 1. Option 2, create a new .c file, put your function into that, and put the .c file there. So second option is called adding a new source file. First option is changing existing source file. We'll take the first option right now. Since we are doing it for the first time, we'll take the first option. The reason for that is if you take second option, When the kernel code is compiled, you must mention that this also should be selected, this.c file. So that requires changing some scripts called make scripts. Right now we are not focusing on the make scripts. That's the reason what we'll do, we'll open the existing source file and add it to that. So what I'm doing, I've taken this file because I'm sure that this source file always will be compiled, irrespective of the build type. I've taken a source file called sys.c. Where is that? Which branch? Kernel branch. We don't have to understand the existing code. Remember this, we don't have to understand the existing code much unless you're doing something in system call that is relevant to existing code. Our objective here is to test. So simply go to the end of the existing code, append your system call. I've appended my call. You don't have to take that code, you simply take the skeleton. That is how I'm adding the function. ASM linkage signature we have fixed earlier, isn't it? Integer type of return and then void the argument type. And then open and close curly. I've put in some code there because I wanted some functionality to run. I've put in some code for test purposes. Otherwise, always system call will do validations and then call a kernel service. In this case, my objective is to show some result when the call executes. For that purpose, what I'm doing, I'm trying to print all the application PCB list. How do we see this list normally from the user mode? PS command. So in place of PS, similar to PS, we are trying to create a command lsproc. Lsproc should show all the processes currently loaded. So that implementation code is there. Just take down the signature if you want to, opening close curly. But this is the procedure now. Now, 4 steps. Are the 4 steps clear? The last part is now you must compile the kernel code for these changes to go into binary, because you have changed source code. How do you test your changes always when you make changes to source? Compile the source code, create an image, binary image, load that binary image, you can test your changes. So up till here I assume things are clear. Are they clear? Let's quickly run through last set of commands. How do you compile this into kernel image? You must compile this into what? A new kernel image. Take down. Next slide heading. This you must carry out. This is your exercise, beginners. Mandatory exercise, this one. Compiling Linux kernel 3, building Linux image. Building Linux image using kernel source 3.2.x. Building Linux image using kernel source 3.2.x. We'll be issuing some commands and talk in detail about what these commands do internally and all that. We'll be carrying out the build process many times, but this is the first time, so basic commands I'll show you. Stick to only commands for the time being. You must be in the present working directory, which is kernel source home folder. If you do ls, you can find all the branches. These commands will work only if your directory is kernel source home. If you come out one directory or if you step into some other branch, these commands will not work. So these commands will work only in this kernel source root. We call it as source root because that is where the kernel source starts. Okay? So these commands will work only here. One step that way or this way, into branch or outside that particular tree, these commands will not work. Let's take down the steps. Step 1, kernel build. Step 1, assumption is your present working directory is source root. Step 1, assign a build. Assign build name. Assign build name. See, if you have a .c file and if you are to add 10 features to it, one after the other, and test each of them separately. Say, first feature modified, you compile and build. Then again open source code, second feature added, compile and build, test. Third, compile and build. Like this, if you do 10 times, you'll have 10 exes now. How do you identify which exe is which feature add? You have to assign unique name to your exe, isn't it? The same you should do with this. With this kernel source code, you can create n number of kernel images. So each time you're creating a kernel image, you must have a unique name assigned so that the end executable generated, the end kernel image generated will have a unique build name. So how do you do that? Watch this.
Step 1, how do you do it?
Step 1, you must open a file with the name makefile. You find the file in the same folder. In the same folder, you find the file makefile, open it. In that file, on top you'll find a macro called extraversion. Don't change the rest, keep the rest as they are. Extraversion, assign that whatever text you want to. Whatever value you want, assign the value to extraversion. So extraversion equal to your own value. In my case, what I did, syscon. So after an entire compile process, the end executable will be called Linux 3.2.14.syscon. 3.2.14.syscon. Next time I'm compiling, I'll change syscall to XYZ. It will be then called as 3.2.14.xyz. If you don't want text, you have your own version number. 1.0, 2.0, 10, 3.2.14.1.0. Got it? So this is your build version identifier. You assign whatever you want. If text is easy for you, assign text. If numbers are required, assign numbers. Clear? So that's the first change. So you must assign a value for which one? A macro called extraversion.
Save this file.
Don't touch anything else. Save this file and quit. But this is step 1. So step 1, we have assigned what? A build name. Step 2. I'm just cutting it short because we are doing it for the first time. The objective is to test our system. Next command is, write down the text first. Choose kernel configuration. Choose kernel configuration. Choose kernel configuration. There are many ways to do this. The general preferred option is this. Most developers prefer it, but this is not the only way of doing it. We'll talk about all the possibilities in the second build when we carry out the build again later. I'm issuing a command called make space menu config. This command will run some script. It will run some script and throw a dialog box. But that dialog box will show up all the features, all the services currently available in the source code. These drivers are there in source. These file systems are there in source. These protocols are there in source. Now, which one you select and which one you want to compile and take it into your kernel binary, you select those. Those that you don't want, leave it out. So this is a menu where you can make choices of what you want to include, what you want to exclude. The source code is huge. Doesn't mean that the entire source code is to be built always, isn't it? It depends on what you need. And what you need, you can do that selection when you know which platform you're building for. In this case, we are building for testing system call, isn't it? So beginners, if you're curious, go into each of these menu branches, look into various options you have, just browse through it. Even if you don't understand few names here, don't worry much, just browse through it. But don't make any changes, because our objective is not to build a custom kernel now. When you have to build a custom kernel, we'll have to make selections based on the platform configurations. That we'll be doing later. Right now, the objective is to add system call. So generate this menu, browse through it if you want to browse through it. But after that, exit will ask you to save, just save the configuration. I've done exit. What it does, it will save the default choices. Because I've not made any changes, default choices will be there. The default choices are saved in a file called .config. You don't have to open this, I'm just showing you. Because this file will be created with what? Automatically generated configuration for your kernel. So these are some features you have selected. I'll help you out understanding all this slowly. For the first time,
Our job is to carry on.
so Menu config, look through whatever is there if you want to, quit, exit. Once you exit, a file called .config will be available. That is required for us. So why are we doing menu config now? To generate that file? .config. Now the step 3. Initiate kernel build. Initiate kernel build. Assuming that you have multi-core hardware, do this. Make -J4. -J4 will speed up the build process by running it in parallel threads. Otherwise, you can just give make also. That will now take 20 to 40 minutes depending on your machine configuration. It will compile the sources that you have selected, which includes subsys.c by default, and build a kernel image for us. So by the time the prompt returns, you'll have the kernel image ready. Your next command should be, just take down the commands as of now. We'll explain more about the impact of the internal script. Next command, when the make -J4 returns, the prompt comes back to the next command.
Make modules.
Make modules underscore install. Make modules underscore install. You can use ampersand and join this earlier than this one. All those are optimizations. First time you carry out step by step. Make modules install. And last one, when make modules install returns, the last command, make install. So 5 steps: build name, configuration, kernel build, modules install, make install. Okay? After make install, if you reboot your machine, at the boot prompt, they will show you how many kernels you have. How do you identify your kernel now? The build name. It will appear with the build name. You select the build name that you have assigned, that kernel will boot in place of default that you have installed. This will not disturb, nor it will override your default settings. So you don't have to worry about the default kernel installed while installing your distribution. It will not disturb any of your default settings. It will only add one new kernel image of 1.5 MB, not more than 1 or 2 MB of space. The rest of disk and applications are same. They will not be touched. So carry out this, and then we'll look at the test process next session. I've got the kernel ready actually here. I simply have to boot and run the application and show you system call result. I'll do that in